All right, let's get started with lecture 5. We're pretty much halfway through the course and the quarter. So we've been talking about the time-independent Schrodinger equation, right? So we said there is an equation known as the time-dependent Schrodinger equation, which in general governs the dynamics of the wave function. The wave function was this object that when you squared it told us about the probability of finding the particle in various places. So we had Schrodinger, which is I h bar, the derivative with respect to time of this wave function, which is a function of position and time. It's a function of position that's changing also as a function of time as the system evolves, is the Hamiltonian operator, which had 2 part minus h bar squared over 2m, second derivative with respect to position, so that corresponded to the kinetic energy plus the potential energy part. And this whole operator acts on this wave function. And then we talked about stationary solutions, which give a constant psi of x of t absolute value squared. So absolute value squared, which is the probability density, is independent of time. And these were of the form where the time dependence is just the exponential of a purely imaginary number. Where E is the energy, and the equation that kind of governs these is known as the time-independent Schrodinger equation. Which is basically the same operator, the same energy operator. Second derivative with respect to position plus v of x. Now acting on this psi of x that doesn't depend on time, it's just a function of position, it's a stationary state, is E, that energy, times psi of x. So a big part of quantum mechanics is solving this equation, this time-independent equation, for different potentials. So when a particle is placed in a particular potential, that's this v of x, it's allowed to have certain stationary states which solve that equation. So the configurations the particle can take such that the probability density doesn't change as a function of time are very special solutions to this equation. And in particular, they're associated with these energies E. So it turns out that E cannot be just any number in general. And those are the allowed energies of that particle. So an example that we started talking about was particle in a box or in an infinite potential well. So basically V of x, if you think about it, the potential, the only thing that determines is these psi's and these e's. That's just a constant operator. It only depends on the mass. V of x it's 0 for x between 0 and a, so 0, a in this region it's 0, and outside it's infinity. Okay, so we talked about some general properties of the wave function, so we wanted the wave function to be continuous. So that gave us the condition that psi of x equals 0 is psi of x equal a is 0, because in the region where the potential is infinite, the wave function has to vanish, right? Because this times that is not infinite. This times this is not infinite. So yeah, so that wave function must be 0 in regions where the potential is diverging. And then we can focus on this region inside the well. And in that region, what is the differential equation? Where, well, v is 0 in that region, so it's just minus h bar squared over 2m. Second derivative with respect to position of psi of x is e times psi x. So what does it mean? It means second derivative. And now, because there is no time dependence, this is just a function of position. I can write it as like a standard d, just second derivative of that function with respect to x is equal to minus 2me over h bar squared times the wave function. So this equation should look familiar, right? When we studied, for example, we studied oscillations, right? We had a form that like the force is proportional to the displacement. So the second derivative of, let's say, position with respect to time was just some negative number times the position. This is the same structure, right? The second derivative of some function of position now with respect to x is some negative number times x. So the general solution we know is going to be a combination of sines and cosines, right? So psi of x in general should be, let's say, a times sine of what? Well, if it's like sine kx, right, then k squared must be equal to that, right? Because the derivative of sine with respect to x becomes k times cosine kx. The derivative of cosine becomes minus k sine kx, and then I get a factor of minus k squared, and that should be equal to that. So we're saying k squared is 2me over h bar squared. So k is square root 2me over h bar, and then plus b cosine. These are the two allowed solutions of the equation. Now, going back to our boundary conditions, so we're now only looking in this region. This general form satisfies the equation, but we must have, well, first psi of 0 is 0. So that means, what does it mean? A times sine 0 plus b times cosine 0 is 0. Sine 0 is 0, so that means nothing. And then cosine 0 is just b, so that means b is equal to 0. Okay, so that's a big simplification. So we know now that psi of x is of this form. Now what can we say? We have to look at the other boundary condition. So what is this guy? It's going to be a sine ka, and that's equal 0. Okay, so we know a is not 0, otherwise the wave function vanishes and all probabilities are 0, so that's not a useful thing, and you can't normalize it. We can't have the condition that's like the integral minus infinity to infinity psi x squared dx is 1, so that the sum of probabilities of the particle being found somewhere is 1. There's 100% probability that the particle exists. So then this sine must be 0, right? So thinking about the sine function, let me draw the unit circle. Sine is the projection on the vertical axis, so it's going to be here, here, here. So any integer multiple of pi has a 0 sign. So that means Ka must be equal to n times pi. We define K as this square root. So that means right, so I just insert this expression for K and I divide both sides by A. Can square, I get 2me is n squared pi squared h bar squared over a squared. So then the energy, or E, this number, becomes n squared pi squared h bar squared over 2m a squared. If you recall that h bar was h over 2 pi, we can also write it in terms of h, and that cancels this pi squared. So, and see, it depends on this integer n, so let's call it en. H squared over, now we get 2 squared is 4 times 2 is 8. That's also, I mean, these are the same thing. So see what happens. So basically we solved this differential equation. We guaranteed that the boundary conditions are correct. We wrote the general form. And then we found that only certain energies are allowed. So if I write it as, the energy operator, let's call it H, right? Which is this thing, minus h bar squared second derivative plus the potential, and the potential is 0 here in this region, it's infinity outside. So that's the energy operator of the entire system, of the particle in that potential, times psi n of x, right? These are the allowed solutions, is some energy psi n. And we found that these energies are certain values, they can't be anything, they're that. And then for each energy, there is a psi n, which is some number. Times sine. Let's say kn times x, and kn is square root 2m en over h bar. So we can plug that in and see what that is in terms of the original parameters. So 2men is going to be, the 2m cancels out, and everything is a squared, so it becomes n pi h bar over a h bar. So it's just n pi over a. So let's take a look at that. So if n is equal to 1, for example, it's sine of pi x over a. So when x reaches a, your phase goes up to pi, so it's half of a wavelength. So it's going to look like that. If n is 2, we have 1 full wavelength inside the well. And n equal 3, we have 3 of these, etc. So those are the allowed stationary state wave functions, and associated to each of them is some energy, and that energy basically goes up proportional to n squared for this particular potential. So E is E1, for example. Here E2 is, because it's proportional to n squared, is going to be 4E1, right? And E1, if we want to write it, is pi squared h bar squared over 2ma squared. E3 is 9E1, etc. So we have certain allowed energies for these stationary states. And associated to each one of them is one wave function. And now, if you want to think about a more general kind of time-dependent solution, it turns out that any linear combination of time-dependent stationary states is a solution to the time-dependent Schrodinger equation. So going back to time-dependent Schrodinger equation, can be like C1 psi 1 of x e to the minus it over h bar E1, where c is just some number, plus some other number psi 2 of x to the minus it over h bar E2, plus some other number and you can go all the way to infinity, right? Because each of these, right, each of these is a solution to the time-dependent Schrodinger equation. And then the time-dependent Schrodinger equation, this guy is linear, so if you have one solution, the sum is also a solution. You just plug it in, right, and add them up. So if I have, for example, IH bar derivative with respect to time of, let's say, psi 1 of x and t is this h operator times psi 1 of x and t, and IH bar derivative with respect to time of psi 2 of x and t is h times psi 2 of x and t. If I just add these two equations, I get IH bar derivative with respect to time of psi 1 plus psi 2. Again, I add these, factor out this operator. It has derivatives and functions, etc. But the sum of the operator acting on these two functions is the operator acting on some of the two functions. We can distribute it through. So if you have two solutions, then their sum or any linear combination of them is a solution. So that's the most general form. And in the last homework, for example, you were handed some wave function and you were asked to calculate some properties of it. It had this kind of form, right? So that wave function would have been a valid solution to the time-dependent Schrodinger equation with this particular potential. Okay. So that was one example of particle in the box. As I said, a big chunk of quantum mechanics is finding these stationary states because, first, I mean, they're important of their own rights. They tell us about, let's say, allowed energies and allowed kind of equilibrium states of, for example, an atom or a molecule, etc. And then they correspond to the spectrum of light emitted by an atom. So, for example, if an atom has certain allowed energies, then we know when it emits a photon, it's because it was in some excited state with, let's say, energy E2, and then it decayed into a lower energy state, but then the energy of the photon that gets emitted because of the conservation of energy must be equal to the difference between these two energies. So you can solve the time-independent Schrodinger equation for more complicated potentials corresponding to like a big atom. And if you find the energies, then you know that the differences are what you would observe experimentally if you analyze the spectrum or the frequencies in the light emitted by that atom. So these energies have very direct kind of experimental consequences. Okay, so far we've been talking about one-dimensional systems. So we only gave one example, particle in a box in one dimension. Another very important example is called the quantum harmonic oscillator. So notice we're doing a different potential, right? It's the same type of problem. We want to find solutions to the time-independent Schrodinger equation. We want to find these stationary states that have time-independent probability distribution. They factorize into a function of time and a function of position. The function of time has the standard form e to the minus I t over h bar times the energy, and the position-dependent part satisfies the time-independent Schrodinger equation. So the only thing that changes is, of course, this v of x, right? So these types of problems in 1D are defined by what the potential is. The kinetic energy part is always this thing, and we want to see what potential corresponds to a harmonic oscillator, and then we talk about the solution. So again, the allowed energies and the form of these stationary state wave functions. And we don't go into the details, so I don't want to derive the solution to this problem. It's a more difficult differential equation. But we just state it and write the result and maybe check that it works. Okay? So let's distinguish between these two examples in one dimension. So here, if you think about v of x, the potential, it's something like this, right? It's infinity, infinity, and 0, constant. What was the potential energy for a harmonic oscillator? So going back to classical mechanics or oscillations, etc., if you think about the mass on a spring constant k, we found that the potential energy is 1/2 times the spring constant times displacement squared, right? So in this case, we have a different potential energy. And if you remember, again, classical oscillations, we had the general form was like sines and cosines of omega t. And omega was square root of k over m. Over mass. So we can alternatively write this in terms of a natural frequency and the mass of the particle. It's a more standard way to write this. It's just some number times displacement squared, a parabolic function of position, but it's more convenient to write it in terms of a natural frequency instead of a spring constant, because as we'll see, many systems exhibit this type of behavior, and there may not be spring really physically in there. Most of the time there isn't in quantum problems. So from this we can write, if I square it, omega squared times m is k spring. So in this case the potential is 1/2 m omega squared x squared. Right, so if you plot v of x, it looks like this. At 0, it's 0. This is x, this is v of x. It's a quadratic some number times some positive number times x squared function of position. So for this one, basically the wave functions we found, right, looked like this. Just goes to 0 here, has a peak in the middle. The next excited one has a node in the middle, goes to 0 in the middle, etc. And somehow this is like it's similar, right? It's a well, except this is like 0 flat at the bottom and suddenly goes to infinity. This goes to infinity, and then only at infinity, at x equal infinity, and it rises up quadratically. But basically, one expects that the particle has more probability to be inside this region, closer to 0, and when you go outside the well in these regions, it somehow decays to 0. So and it turns out, I mean, one can kind of make this guess about the qualitative shape of the solutions. And the shape is going to be kind of similar. So we expect a ground state that looks like this. And it decays to 0. Then maybe a first excited state kind of looks like this. There's a 0 here. And again, when you go outside, you decay to 0. So there is some qualitative similarity between the solutions. Okay, so what we want to do is to solve a different differential equation. Second derivative with respect to position of, let's say, the wave function now, plus the potential, which in this case for the harmonic oscillator is 1/2 m omega squared x squared. That multiplies the wave function, is again some energy times the wave function. Okay, so we're interested in allowed energies En and corresponding psi n's that satisfy this equation. By the way, the simple harmonic oscillator, this problem that we're discussing here, if you want to read about it in the book, it's discussed in section 5.7 of the textbook by Harris. So let me put a note here. 5.7 of Harris Modern Physics. So in the same way that for a particle in a box, right, that was a different potential, it was 0 in a region and infinity outside that region. This is a different potential. It's a parabolic curve in the entire space. For the same way that we managed to find an exact solution, namely we found the allowed energies En, and we found the corresponding wave functions, we can solve this equation exactly. The solution is a little bit more complicated, so I won't go through the derivation here. I'll just give you the results. All right, so the energies are very simple. So let me make this table. So we have En and we have psi n. So the energy is in general h bar omega n plus a half. So it's just a simple linear function of integer n. So n can be 0. So for example, we have, let's say here we have n. So then en becomes just h bar omega over 2. And then the corresponding wave function, again, qualitatively, we know how it should behave, right? It has a peak at x equals 0, and then when you go to x equals plus and minus infinity, it decays to 0. So it's going to look like this. If 0 is here, has a peak here, and then decays. And the equation for psi 0, let me write it here, is going to be I write it in terms of a parameter b that I haven't defined. I'll just define it in 1 second. So it's going to be b over square root pi. And this is already normalized. So the integral of psi n squared dx is 1 from minus infinity to infinity. One half b squared x squared. Okay, and b is given by square root of m omega over h bar. H bar is under the square root here. So it's a Gaussian, and it decays to 0 at x equal infinity, and sort of you can see the interpretation of b. So basically 1 over b has units of length, so length, right? Because the argument of the exponential is dimensionless. Now, and then, you know, when this thing becomes very small is when b times x which is a dimensionless number, is large enough. It's much larger than 1. So kind of if this Gaussian has some characteristic width where the wave function is big, that roughly is proportional to 1 over b. Okay. We can also check the dimensions more explicitly. We know h bar omega has units of energy, right? So let's think about the units a little bit on the side here. So omega has units of 1 over time, right? It's a frequency. Mass is, of course, mass. It has units of mass. And we know h bar omega has units of energy. Energy, think about kinetic energy, so 1/2 mv squared. So it's going to be m, and velocity is a length over time, so L squared over T squared. Okay, so if I want to think about B, so I know omega has units of 1 over T, so H bar has units of mass L squared over T. Okay, so putting this together, what are the units of B? M omega over h bar. That gives me m over t over h bar, so it gives me t over ml squared, square root. M cancels with m, t cancels with t, so that has units of 1 over length, as expected. So this is bx is a dimensionless quantity. 1 over b has units of length, and it's a characteristic width of this Gaussian. So if you make b larger, for example, if you make omega larger, let's say, or the mass larger, 1 over b shrinks and you get kind of a more pronounced peak. Okay, so then we can continue with this structure. So let's say n is equal 1, E1 becomes 1 plus a half is 3 halves. And then, so let's call this psi 0. Psi 1 becomes a polynomial times the same Gaussian. So that's the general structure. It's a polynomial, and they're known as Hermite polynomials. So the constant up front is b over 2 square root of pi 1/2. Then we have 2bx. And it's a polynomial of bx. Bx is a dimensionless quantity. The same exponential factor. So this thing will look like this. If this is 0, it goes up, comes back to 0 at 0, has a node at 0, and then goes here and again becomes negative and decays to 0. Well, this is minus this, right? If you multiply x by that Gaussian, I guess on this side you're going to get the positive, on this side you're going to get the negative. But it doesn't matter. It's up to a sign. That's the general structure of the wave function. So similarly, remember for particle in a box, the first excited state also was a full period of a sine function, right? It went up, had a node in the middle, went up again. Right, it looked like that. So qualitatively, there's quite a bit of similarity between these wave functions. Anyway, so basically the next one is a quadratic polynomial, and it has 2 nodes. The next one is a cubic polynomial times the same exponential. So let me also write the next one, and I stop there. Basically, these polynomials are characterized in multiple ways. You can get the coefficients from a recursion relation, or you can, there are various ways to extract them. They're available in tables, but that's the general solution of this differential equation. And the energies themselves are really simple, so we can that's the result we should remember, basically. This h bar omega n plus a half, this linear relationship. And then we kind of know the structure of the wave function and their qualitative behavior, but we don't need to remember these. We can just look them up if necessary. So the second excited state, so this is a ground state, this is the first excited state, the second excited state, this one is going to be, there's again some normalization in front, b over 8 square root pi to the 1/2, then 4b squared x squared minus 2. So that's a second order polynomial, and it turns out these guys only have even powers when n is even, and when n is odd we only have odd powers. So the functions are an even function, an odd function, an even function. So this looks like something like this, right? Has a peak in the middle, goes down, decays, goes down, turns around, decays. All right, so this is nice. The harmonic oscillator is exactly solvable. It's a potential that we can solve exactly, find all the energies and all the wave functions for stationary states. But it actually turns out to be extremely important and ubiquitous. And the reason is we may not, like in a molecule or an atom or some quantum mechanical system, we don't have springs and masses. But the point is that any potential arising from any kind of interaction, any kind of energy, if you look around the minimum, the harmonic oscillator is a good approximation. So consider some kind of arbitrary potential. With a minimum. So let's say this is x, we have some v of x that does something. For example, like that. Yeah, let me make it smoother here. It's something like this. And you're interested in the lowest energy state. So those are energies closer to the minimum of the potential, that the minimum, let's say, occurs here. And, well, regardless of what the shape of this potential is, when you're close to this minimum, you're in this region around the minimum, a harmonic oscillator is a very good approximation to this. The reason is this. So suppose, you match the value, right? So if you just match the value, you can imagine a constant that's sitting at the value of the potential at that minimum. So that's like one level of approximation. And this actually matches both the value and the first derivative, right? Because at the minimum, the first derivative is 0. So let's call that point x0. And we know that dv dx at x0 is 0, right? Because it's a minimum, the derivative must be 0. So that constant, and this value, let's say, is v of x0, right? So that's like the 0th order or first order approximation to this. But we can consider a quadratic curve, something that curves up here. So that's a much better approximation, which matches not only the value at this point and the first derivative, which is 0, but also the second derivative. So how do I do that? Well, let me just write it. So if I write this v tilde of x to be v of x0 plus second derivative of v with respect to x, so the second derivative at this point calculated at x0 times a half times x minus x naught quantity squared. Okay, so I know at x equal x naught, what are the things I can say? V tilde of x naught. X minus x naught is 0, so it's going to be v of x naught. The value matches. First derivative at x naught. What is the first derivative? So let me first do it in general and then put the value of x naught. So first derivative is going to be, this is a constant, doesn't depend on x, so it goes away. The only dependence is in this x minus x naught. So if I take the derivative, I get a factor of 2, which kills that 1/2. So it's going to be the second derivative calculated at x naught times x minus x naught. We put x equal x naught again, this coefficient kills it, so we get 0. Calculate. So therefore, let's say dv dx of v tilde at x naught is 0. If I do the second derivative, you can imagine this is a general form, so the second derivative, x minus x naught gives me 1, and then this is a constant that remains. So it's the same as the second derivative of Vx around that point. So for people who are familiar with Taylor expansion, we mentioned it before a little bit. We can basically approximate any function around any point as a power series that depends on its various derivatives. So this is really nothing but keeping the first couple of terms in a Taylor expansion. So in general, we know that v of x is going to be v of x naught plus, I call it v prime, first derivative, at x naught, x minus x naught plus 1/2 the second derivative, this thing squared, plus 1/3 factorial the third derivative, cubed, etc. And then when x is close to x naught, this is small, so higher powers of something small will be even smaller. So if you're in that region, it's acceptable to truncate this series at some order, and then this gives a very good approximation to the potential in that region. And then it allows us to, for example, use the harmonic oscillator energies to approximate the ground state energy of that arbitrary potential. So in your homework, you have a similar problem where you're given some potential for a diatomic molecule, and you're asked to estimate using this method the lowest energy. Let me give you one example. Do the same thing for one potential. Examples always help. So example, let's say v of x is alpha x squared plus or minus alpha x squared plus beta x to the fourth. So what does this potential, and we want, let's say, estimate the ground state energy. So how does it work? Well, we know at x equals 0, we have a maximum. So the potential, if I look at v of x, will be something like this. It's a double well. So this is 0. Where are these minima? So we have to see where the derivative is 0. So the first derivative is going to be minus 2 alpha x plus 4 beta x cubed. And if I set it to 0, right, x naught is here, and also there's going to be a negative number, as you'll see in a second, is minus 2 alpha x plus 4 beta x naught squared times x naught. So I factor out the x naught. It's going to be minus 2x naught alpha minus 2 beta x naught squared. So we see the derivative vanishes at x naught equals 0, which is here. That turns out to be a maximum. And it also vanishes at x naught squared equal alpha over 2 beta. Okay? So here we have square root of alpha over 2 beta. Here we have minus square root of alpha over 2 beta. Now, if I want to find a parabolic approximation to my potential in that region, well, how do I find it? I just need to match the second derivative. So let's find the second derivative at x naught, or second derivative at x. I take one more derivative. It's going to be minus 2 alpha plus 12 beta x squared. And second derivative at x naught, which describes really the curvature at that point around the minimum, is going to be minus 2 alpha plus 12 beta alpha over 2 beta, right? X naught squared is that. So that gives me 12 over 2 is 6, betas cancel, so 6 minus 2 is 4. So I think that's the correct answer. And then what is the approximation? Well, V of x around minimum, let's call it V tilde. That's how I approximate my potential, is going to be V of x naught plus 1/2 second derivative at x naught times x minus x naught squared. Okay, so I've added some constant to the energy, and then I have this potential here, right? And if you call x minus x naught, let's call it z. We make just a change of variables. Again, the derivative with respect to x is the same as derivative with respect to x naught, so the kinetic energy term kind of it's not changing in the Hamiltonian upon this change of variable. So the ground state energy corresponding to this potential, we expect it to be V of x naught, which we can calculate. We can put this value into V, and we're going to get something that depends on alpha and beta, plus h bar omega over 2, right? So what is omega? Remember, in a harmonic oscillator, we have V of x is 1/2 m omega squared x squared. So omega comes from this, right? So m omega squared is basically identified with V double prime, which is 4 alpha. So from here, we get like the effective omega for this particular potential to be square root of 4 alpha over m. So we can put that in, and then as a function of h bar, mass, and alpha and beta, we have a good approximation for the energy of the ground state. Let me just quickly calculate V of x naught here. So V of x naught, we have minus alpha x squared plus beta x to the 4th, right? So we know x naught squared is alpha over 2 beta. So this is minus alpha over 2 beta plus beta, alpha over 2 beta quantity squared. So this becomes minus alpha squared over 2 beta plus alpha squared over 4 beta, right? 2 squared is 4, beta squared cancels one of these, alpha squared, sorry, here. So this is minus alpha squared over 4 beta. So our energy estimate becomes minus alpha squared over 4 beta plus h bar over 2 square root of 4 alpha over m. And this would better have units of energy, right? So if we think about energy, we know V has units of energy. So alpha has units of energy over length squared, beta has units of energy over x to the 4th, right? So here I have alpha squared. So alpha squared will be energy over length to the 4th divided by energy over length to the 4th. Yeah, let's do this. Alpha has energy over length squared. So alpha squared has units of energy squared over length to the 4th. Beta has units of energy over length to the 4th. So alpha squared over beta has units of energy, right? Length to the 4th cancels out. Here we have energy squared divided by energy. So that's good. Let's also check that this thing works. So units of h bar we calculated before, we know h bar times omega is an energy. So h bar has units of energy times time, if you wish. So let's do this. So h bar is energy times time. Alpha has units of, as we said, energy over length squared, if I just take the square root. Yeah. Therefore, alpha over m has units of, let's write the energy as m. So think about kinetic energy again, mv squared. So it's L over T squared. L squared. M is mass. So this has units of L squared cancels with L squared, M cancels with M. So that's 1 over T squared. And alpha over M square root has units of 1 over time. Then that's good, right? H bar is energy times time. It cancels out the time. So this term also has units of energy. And the units check out. All right, so this is a good place to stop. And I'll see you in the next lecture.